Okay. Let's continue. So everything what is on the board so far is just I'm trying to explain you what kind of pictorial or algebraic language you can write down out of the Poisson structure or out of the quadratic Poisson structure. So the story that you can do is just to start from this picture. If it's quadratic, then it's 2 inputs, 2 outputs. If it's more than quadratic, then the number of outputs will be bigger. You have this kind of relation, and you're trying to write down, draw all possible pictures you can write. Now, what algebraic structures are you can get in this story? So the first thing, so what does it mean to draw possible pictures? So you draw kind of pictures. Pictures means you draw the graph, oriented graph. With so in quadratic story, each vertex has 2 inputs and 2 outputs. And you're trying to also with each such a graph, you can assign a tensor which will be called from and now the algebraic structure that enters the game is the following. So a priori, first, what kind of graphs we can consider? So the simplest story is if you consider that just the genus equal to 0, or trees. So if you consider only trees, then everything is fine more or less. And the corresponding algebraic structure has the name diagram. I'll explain in a moment the definitions of those words that I'm using.
What is genus?
Genus of a graph. So you look on the graph. The first Betty number. Groups in the graph. Then the next step is that you can draw arbitrary graph of arbitrary genus. The corresponding algebraic structure is called wheeled operand. Because what you can do, so you can draw like this, you can draw a picture like this.
I wonder whether it's graphless, so you the definition of wheeled operand is just depend on so the usual graph is usually defined without.
I said that I will explain this notion in a moment. I'm just saying that this is just so far the names.
Okay, so just the names.
So far just as the names.
Okay.
Wait a moment. What is important for me that what I can do out of each graph, I can write down a tensor. Now, if I look on this graph like this, so if my graph has loops, wheels, meaning that if I have the directed wheel, directed loop, so that the path, oriented path, which starts in the same point where it ends. What might be the problem on the level of considering of the corresponding tensor? The problem might be if the dimension of the space of V is infinity. Then this kind of taking the loop, meaning that you take the trace of your space. And this is the best thing because it's impossible to take the trace of the infinite dimensional space. So not allowed for some structures on infinite dimensional space. So in order to avoid this kind of story, so you can ask him to avoid the graphs with these directed loops. Those kind of graphs, or graphs without. Graphs without. The corresponding algebraic structure is called program.
Сейчас я выйду.
No, so here it's also better to say. And now let me say a few words about the names. So I promised you just so far these are the names, and now what are the corresponding the definition of those algebraic structures. So the definition, so let me say for this case, and these two are just the two small things for the story. So what you can do, so selection of vector spaces. Plus the composition rules. The composition rule is the following thing. So if you reach so if I consider the graph gamma, which will be, for example, either it will be the graph with the loops, or it will be directed without the just the tree, or it will be without this direction. So what I want to have, I have the following things. So I have to define the composition through this graph, meaning that this will be the tensor product of V inside gamma. The P of like how it works before. So, for example, if if I'm considering this PMM as in my case where M is equal to N equals 2, then for each such a graph, I can define a tensor by taking the corresponding contraction of indices with respect to all edges. And I get the element from here. And so all possible projections of this sort will give me this kind of operations. So you have, so the definition is the following. So you have a collection of those spaces. You have the collection of these kind of homomorphism, which is just the rules how you compose your operations. So you consider this as operation with several inputs, several outputs. These are elements of the taking the composition with respect to a graph, and they have to satisfy associativity. And then equivalence. Associativity means the following. So if you take a big graph and you take a subgraph and you contract this graph, meaning when you do the contraction, meaning that you do this kind of composition. You're taking this kind of story and you get the output. As soon as you contract everything in one vertex, so you have just several inputs, several outputs. And SN equivariance means that this kind of operations is equivalent with respect to action of the SN group of the graph. So this is the data, this is the algebraic structure which I'm interested in. Now the quadratic Poisson structure is a typical element, an example of those stories. Meaning that what we know about this example. So far I'm doing just explaining you the algebraic language, which is nice for this, not to solve some problems about this story. So QP, quadratic Poisson structures. And is what? So you're saying the following thing, more the same method. So you're saying that it is generated by operation in this form, in the form symmetry minus modulo this kind of relation that was on the board. So you see what is nice in this type of presentation is that the relations you have. So you draw all possible graphs out of this story and you write the relations of this kind of sort. These relations are the relations with trees, so there is no genus in this relation. So therefore you are able to define either the dioperate or properate or root properate, whatever you are interested in. So from dioperate relation. Okay. Now I can start to say some results about this story. So first is the kind of ideology in this story. So what if you consider this kind of algebraic structure, so the question people from algebraic topology are typically asking is the question of deformation theory. What happens if you try to deform this algebraic structure? What will happen? Adam, can you say something about the commodity theory about this algebraic structure? Now, in order to say something about this story, so what people do, people try to write down the resolution of this quadratic Poisson structure in the category of either diagrams, improper, whatever, depending on which world you are living. Why this happens? Because so this is just a standard story for the deformation theory, because it's really complicated to deform something where you have really complicated relations. It's a bit more simpler, but practically it's not really simpler, but it's another point of view on the story. You can write down the resolution, so you write down something free, but with a differential. And then you try to deform something free, but the free objects, they are always rigid. So there's no way to deform the free object. But what you can deform the differential. And this is why you are looking for the resolution of the story. Then the question is in which world you are trying to deform the structure. Now the claims here. So this DP, let's say in terms of diameter. I don't want to go to the details, but I think the output of the story, when you people in phenomenological algebra see the kazoo, so the kazoo is the French mathematician who find out a very nice resolution for quadratic algebra. Maybe it's first known for just for functions, but then it really happens now that people really like this story. So you see here. The relations are quadratic, meaning that you have relations for writing the relations, you use your generator twice, meaning that the relation is quadratic. So therefore, saying that this is kazoo, it can be rephrased in the following thing. So I have, in other words, you can say that the resolution looks as follows. So you look on generators with M, the number of inputs equal to the number of outputs, and the differential is some and here you have so you sum up, you split the vertex. Graphically, it's interesting. You have the vertex, you split it into two vertices, and you split in all possible ways the inputs. So here, if you have 1, 2, 3, 4, 5, so here you have.
Just to make sure, in the operator theory, quadratic operator and positive operator defined with the help of quadratic group, and then the question is that the free operator inside of the quadratic group has some differential, and is it the same here?
Yes, absolutely the same theory. If I don't want to go to the details of the Kazin theory, but the idea is absolutely the same. So you start from, so this is kind of diopter, quadratic diopter. You can look on the quadratic dual diopter, which is they have the same list of generators, only one generator, and the relations are the dual set of relations. The kind of dual set of relations for the story meaning that all these kind of monomials are the same. If you draw no possible taus here and sigma, they are more or less the same. And that's precisely what you get out of this story. So what is written here is that generator and the differential is that how this element can be given as a composition of two elements. But you see that, for example, if I have here only 3 inputs and 3 outputs, what I get precisely this kind of relation. Right? So because you can split it only in two, in a unique way, 2 inputs, 2 and 2. One and one because m is greater than 2. One is impossible. So if you have here 3, then it's 2 and 2, and this precisely the relation that you have. So the statement that this diopterate is a Kazoo diopterate means that you have a very simple resolution of this diopterate. So if you want to work kind of information of this story as a diopterate, then you are lucky because it's really touch something. Now, the next statement is, which is more tricky story. In order to prove this statement, you have to work out some Grobny basis machinery to operate. Some technical machinery, but it's not really complicated.
Kind of test similar to
What is the input Kapanov test? Well, it's a complicated test. It's the test that, so the people really try to prove the Kazunus out of some small computations, and this kind of statement is a huge statement about the universe of category. This is the reformulation of this statement. No, that there's for either for operats or also for diopterate, there is just the machinery of how to, if you know the generators and relations, so there's kind of finite data that you can check.
There's kind of Grobny basis.
Yes, there's a kind of Grobny basis story that you can check. If the basis is good, so that for the Kazunas, it's enough to have a quadratic Grobny basis. So if you are able to show that you have quadratic Grobny basis, then you are done. And this is what happens in the story. This is what you can read. Now, the second theorem is that the proper meaning that here and you can say the same story for so you can see all possible graphs out of these kind of generators. You want to show that this still be a resolution of And for the remaining story, which is the most interesting for applications, because typically we are working with finite dimensional space, is the story with the will proper. But for will proper, this is only conjecture. This I'm not able to show. And now, I don't want to go to the details of this proof, but I want to say one comment that at the moment, for those who know and been working with the proper will proper is much more complicated story than the proper. Namely, there is no, at the moment, there is not known any resolution in integral will proper. Any.
Whatsoever, because impossible.
Yes. So there is no. So this is the first example. So there are no non-resolution. So if you're trying to do this kind of search, you start from the diagram. For example, another example of a diagram is a Lie algebra. If you're trying to do the story for Lie algebra, it's known that this one is kazoo, but this one is not kazoo. And there are some more examples. So at the moment, none of examples solve the resolution in this category. It's really complicated question.
I don't quite understand this diagram. So what is on the left?
On the left is just the QP that we have
No,
before.
on the left.
On the left.
Yeah.
Here you consider the free
No, I mean
proper
the free proper this
generated by this kind of Carolas. We have the collection of Carols for each arithmetic greater than equal than 2.
So you mean
Several
this
instances.
is-
The same story as
this is
here.
precisely the Kasunas, right?
Yeah, this is precisely Kazunus.
Okay. So you don't know what, you know any resolution for.
And I don't know any Kazoo will proper.
And even it's like you didn't know any resolution of the group.
Well,
I mean, does the free resolution construction work in something like?
bar for bar construction. That's what. Any touchable, so any
Yeah, okay,
reasonable,
that's the thing.
any minimal resolution is not known. But of course, you can bar to bar construction works here, but you don't know what to do with the story because
It's huge.
It's huge. So okay. So this was a part about the algebraic language, which is important for the rest. But as soon as I have 4 hours, so let me do another story, which is known for another story is deformation. And for the deformation, what do we need to do? So when you have if you start to work with this, if you have a resolution, then you can say something about, first of all, you can say something about Poisson structure, quadratic Poisson structure up to the multiple, because this is a kind of, if you have a resolution, then we can say that the quadratic Poisson structure up to the multiple is a representation of this kind of dioperate, wheeled operate, properate, or which category you're considering. What does it mean? It means that you have a collection of tensors with this kind of property. So before I have only 2 inputs and 2 outputs, and now I'm saying that I have a lot of tensors with the following that satisfy this kind of differential. So if you look, so that this, if you look on the representation, following sources, E with down. So this is a part of the polyvector fields on the homogeneous. Alright, so you can think about this representation as the following algebraic structure. So you consider some vector space V, maybe with a differential. Consider polyvector fields on it. You consider the collection of homogeneous polyvector fields, meaning that when you scalar the coordinates, then it remains the same, because if you multiply V to lambda V, then here V also goes to lambda V, and this term at the end remains to be the same. And you satisfy this kind of relation here, let's put the total bracket at the bottom. P2 plus 1. Okay. And now, what people do next in opera theory, they are considering, so when we have the expression is the following piece. If you're considering this map for this one, QP infinity will be just and you're trying to look at the deformations of this map of the resolution. So this is more or less the same as saying that you are looking for the deformation of an identity functor, and this kind of deformations is an automorphism of this algebraic structure. And this can be computed directly.
What does it have to do with properties? Oh, it's just.
It depends on which category you consider. So you can look at this deformation in all possible stories, either in the dial product, or in the pro product, or in the wheel product. The answer will be different, because you are trying to deform the structure in the corresponding category, either in the category of dial products, or in the category of pro products, or in the category.
Trying to deform this map?
Yes, you're trying to deform this map. More or less, you're trying to deform just the identity map. Because this is, on the homotoptical level, this is just the identity map. So you're trying to deform the identity map. This is a kind of automorphism of the structure, the derivations of the structure of this QP. In order to compute it directly, you need to have with a free resolution, because whenever you have this free resolution, then you can, then the complex is threshold. So this complex will be just form from the cell times the cell.
Some kind of model structure.
Yes. You can do it. You can use the model structure indicating proper.
We said that you don't know if this
Yes, that's the problem. But you can deform this kind of map, right? Just so you can look on this kind of map. Hopefully, this will be the resolution. Now let me mention the answer that we have here.
Sorry, once again, what is QP infinity?
QP infinity is this kind of story.
Yeah.
So I define them in the following way, and even here for the will property, I do the same story. The free will property generated by this Carolus yielding this kind of relations. Infinity in order to show that this is a free this resolution. Okay. Now this theorem. To myself and that information in the category of properties. So I have two questions. Information on this map in the category will properties. Here is so it's one that I want to GC2.
What do you call definition here? Is it just some homotopy equivalent maps?
There's a well notion of the deformation complex, where just the elements of this complex are given by the story, and the differential is given by the just the co-unit and the unit, so the co-bar construction. I don't want to go to the details of the story because it's really long story. I just want to mention, then I will show how why it's interesting for applications.
I know the notion of deformation complex, but not forward. So
no, the differential complex forwards it's a long story and complicated story. Let me sweep it under the carpet. So I'm saying that there is a well-defined notion of the differential this structure, this algebraic structure. Such that, and then the theorem for you will be this black box from the left. There is a working for some black box on the right.
Yeah, this looks mysterious in this way. But just before proceed, then is it true to before you believe that what you do is just kind of take some resolution on the left, take a resolution on the right, and then the information complex is mapped between.
You don't need to take a resolution on the left.
So just
take a resolution on the left.
Okay.
Yeah, then this resolution is the free construction of some co-operators. Then you're looking for the maps from this co-operator itself.
Free operate from free operate from co-operate. From dual operate.
Yeah, free operate from the dual co-operators. And then when you deform the complex, when you deform the maps from something free, as I said, it's mean that you deform the differential.
Yeah.
When you deform the differential, mean that you deform the map from the generators to the right hand side.
Just like anything else.
Yes. So now you are looking for the maps from generators to the right hand side. And the question is how to define the differential. The differential is hidden in the proper structure here or here. Do maybe it's better.
And no infinity.
This one is always comparing.
Oh, yeah, that's
As you
okay.
want.
Okay. Yeah, let's decide what the number.
These generators are the elements of the dual.
Yeah. Just decide.
Yes. So I'm saying that there are some results about how to deform this algebraic structure, and the deformation of this algebraic structure can be quasi-isomorphic to some well-known combinatorial complexes, which is called the graph complex of Kontsevich. 2 and 1 are some indices, and then now I want to go to the story because it's a separate story, but it's everything behind, and that's why you can enter the story about the deformation of quantization. Okay, so now you can forget for a moment about this proper blah. Now, let me see. This graph complex is the following thing. So I define you now only the combinatorial data. So you are looking for the span of all graphs. Where you have so you have the ordering of vertices. Those matter to have the rotations. And therefore you have the action of Xn, M, to the power right, Sn x on vertices, Sm x on edges, S2 x on the rotations of the when you say that here you need sin E sin 1. So I mean, I'm considering how it works. You are looking for a graph. You first order all vertices, you order all edges. And you identify graphs where this numbering is different by the signs. You identify by this with respect of the signs where D responds to this image D,
So, what is it sign?
Meaning that for D even, this is trivial representation, for D odd, this is sign representation.
I see.
The tensor power of the sign representation. So I need the graphs with the same numbering of input of vertices and edges that differs one from each other by the numbering of vertices and edges should differ by a sign. The sign rules are a bit tricky, but let me also spell them under the carpet. So, but what you can do, so you're saying that after all, so you can look on a graph, erase all possible numberings, and this gives you an element in this graph complex. Maybe this will be 0, because, for example, this kind of symmetry, saying that this graph is the same as graph, but with the opposite, with a minus sign. But more typically, it's not 0. And then, so these are graphs, and then I want to have the differential. So I want to say the degree of vertex equal to D, degree of H. And differential is once again a vertex split in differential. So we need some possible. So we split the vertex into vertices and what and split the edges in all possible ways. Also, important is that greater than 3, where all vertices when it's greater than 3. Therefore, when we have this kind of condition, when all vertices has values greater equal than 3, this implies that GC free of each concrete. So first of all, with the genus G, you see that the differential doesn't change the genus of a graph. So you split one vertex, so you add one edge and one vertex, so therefore the earlier characteristic doesn't change.
Can we just insert one vertex in between? So can you draw it over there?
So I have one
vertex. You just split the vertex.
I split a vertex splitting. So you split a vertex. So the dual operation is just a contraction of the edge. Maybe it's more simple way to learn the story. So you have this is a cosmological complex, and the dual complex will be just the contraction of the edge. But you see, when you contract the edge, the genus doesn't change. Therefore, this GC is equal to the sum of the genus G. Sum of loops. And what is nice that each component, each direct summand, when you fix the genus and each vertex has values at least 3, then this one is finite dimensional.
All is finite dimensional?
No, just the complex itself is finite dimensional.
Finite number of graphs?
There are finite number of graphs.
With the prescribed number of loops?
With the prescribed number of loops. Yes, such that each vertex is at least trivalent. This is the key point. So if you have vertices that are bivalent or one or univalent, then of course it's infinite dimensional. But when the number of vertices, number of valences of each vertex is greater than 3, then the number of those graphs is bounded. And therefore your questions also to look on this problem. So for each, so you can compute by computer just for each given group number and each given homology this complex. And this complex or this homology is really interesting for the people from deformation theory because it's really a lot of questions under the story. So some remarks on that. For example, H1 of G2 is conjecture equal to 0. So this is a conjecture. But if you know this story, then this will imply, for example, the information. The existence of information. And the most mysterious part is H0, which is also like, so it's another name called like Müller group, the algebra. And this is the conjecture that this is the 3D algebra. Of infinite number of variables of all possible forms.
It can be also conjecture.
This conjecture, no, this. So this story, the GRT is equal to this story. This is called the Greenfield conjecture, and the result that H0 is equal to GRT. This is the result of Thomas V. Weicher.
GRT is cosine.
The GRT, yeah, cosine type Müller the algebra, which corresponds to what is this GRT? It's a long story.
Long story. And on the right, don't see.
On the right, is the free algebra generated by known the beginning of the story. So there's really big story behind of this graph complex, and people are really interested in the model. Now let me say a few words how to connect this story with this Poisson structures. First of all, yes, show the action. There is an infinitesimal action which is given by the following things. So you take the graph gamma from here, and what you can do some of this kind of inputs and outputs. How can I act by in a graph in this picture? I can do the following things. I can give my graph gamma, and I can place in each vertex all possible orientations. And I'm claiming that this is an infinitesimal action. So this is precise action of the E algebra of the structure of the Poisson structure. If we start from E and enter the elements from E into the graph, and then you exponentiate this story, right? With E plus h to the power of number gamma. Then this will be Poisson structure. If I suppose my gamma was gamma is a graph, then what I can do, I want to replace the initial tensor as a Poisson structure by a new tensor. What I'm doing, I'm placing my P in each vertex of a graph, and I'm drawing the inputs and outputs in all possible ways, such that for example, if P was the number of inputs and the number of outputs will be as much as I need.
What do you mean? You put, of course, P is quadratic. You cannot put in non-quadratic.
Yes, but I have the additional frequencies that drawing all possible outgoing and ingoing edges. So here each vertex is three-variant, right? So for example, so therefore I can, for a quadratic story, I can write, for example,
So add one more vertex. And then
no, it's not vertex.
add one more edge.
Edge.
Yeah, you get one more edge.
In each vertex, and draw and try to choose
the
the possible directions such that in each vertex I have two inputs and two outputs.
Yeah. Is it always possible?
Not always. Sometimes it's possible, and sometimes it's given the challenge. And out of the story, you can write down a tensor.
And yeah, just
So, for example, here, what you will get, I'm claiming that you will get once again the tensor with two inputs and two outputs. Let me do in this picture, so like this. Here, one inputs, 2 outputs, 2 inputs, 2 outputs, right? 2 inputs, 2 outputs. So if you start from then you get a new thing like this. And this is a kind of infinitesimal action, meaning that p plus epsilon on the graph with this story will be a new Poisson vector. So if p satisfies the structure that is in Poisson, then this sum also will be infinitesimal Poisson structure.
Infinitesimal in the sense that these
Plus epsilon, yeah. No, that means that if you want to be the real Poisson structure, you have to exponentiate this. This is, so you have to apply not the gamma itself, but the sum of the group, the corresponding group action. So you have to write down sum of gamma to the power n.
power of graph is
no, you have the action of each gamma, so you can exponentiate the action. Yes, that's true.
So you fix the graph.
Yeah, you fix the graph.
Then we have this action. Or you write over this fixed graph, and then exponentiate this action.
Yes. And then you get a new Poisson structure. That's the way. The classics, and that's people believe that these are the all possible informations of the Poisson structure.
It has something to do with authentic
Yes. H0 of GC2 is
H0.
Yes, that's precisely the action of this. So this is a kind of combinatorial way of the action of GRT. The problem here is people do not know really the representatives of these cocycles, of the sigma 3, sigma 5, and so on. These representatives, if you write down them in a graph, so the only known thing contains some multiple zeta values. So the only people knew only this. We say the tetrahedron. The next one will be something like this plus some term.
And this term is not known?
No, for sigma 5, so up to some degree, the computer was able to compute those elements.
Always computed.
Yes, but I don't know, it's maybe at the moment up to 30 or something like that. So it's the dimension. But the people do not know that do not suggest the formulas for the representatives of those sigmas, so that people knew that there is an invariant from the right hand side to the left hand side. But how to find the generators on the left hand side using this kind of stuff now? Not know.
I mean, the second, this pentagonal diagram cannot be used to deform the quadratic Poisson structure, right?
No, it can, because there's another term. There's another term like
So
this.
I mean, the second term is possibly impossible.
Yeah. This term doesn't affect. You're right. But the second term really affects. And there's always, for these terms like this, and this follows from our result, that there are terms with only 3 or 4 valid vertices. So each cycle here really has to contain the term, non-zero term with 3 valid and 4 valid vertices, which will really act non-trivially on this quadratic Poisson structure.
What about the linear Poisson structure? Affected by the form?
The linear, the only known deformation of the linear Poisson structure is the universal velocity.
That's why I was asking. And you know, the name of this day of this seminar is after all quantity, so right?
Yes, so that's maybe it's better to say it in the beginning that if you try to deform the constant Poisson structure, you get the Boyle problem. If you try to deform the linear Poisson structure, you know, you get the universal velocity. And claim that I want to say is that the deformation, if you try to deform the quadratic Poisson structure, then this the story as rich as for arbitrary Poisson structure. Okay, so now it depends how much steps are till 8 or till
Actually, depends. Officially, our seminar is still 8:30, 7:30. But if you have some interesting details, you're free to talk about 8.
okay, it depends on the listeners. So if there's a lot of story behind, so I can continue, but maybe
Okay, let us say then 15 minutes at least. Okay.
15 minutes. Okay, so let me try to explain a bit more about this graph concept. And the deformation, so the relationship between the graph complex and Poisson structure. The first story is that it's X, and in some sense, this action is on the homotoppical level, this action, faithful action. The problem is people haven't really seen how this simulate action works, because you see that even for the simplest cocycle, for this tetrahedron, the formulas are really huge. So you really have to sum up to 8 terms, and people, I haven't seen the works where it was written that here is the Poisson structure, how you deform it, and you get another Poisson structure, which is homotopically unequivalent to the simplest. But what you can do if you continue to work with pictorial language, if you continue to do this story and graphs, let me say a bit more, using a kind of different language, but practically this language is more or less the same if you work out all the details. So let me look on the polyvector fields. Over metrical E times star. This is from what we started, more or less. And this is a Lie algebra with scope inverted. And T, the value of here is a constant element. This algebra. Right, because P is an element of degree, so the degree corresponds to the degree of number of vectors, so the excesses size, so the degree corresponds, the homological degree corresponds to the number of D's minus 1. The relation that we have before is P is equal to 0 is precisely the Walker annotation. Now, if you want to say something about this story about the elements of how to deform them, you have to know the Lie algebraic homology of these polyvector fields. deformations of the story, so we're interested in the joint coefficients in the joint representation. This is response to the deformation of this Poisson of the liberated structure, and how you can form it, or you can totally form the differential. You can add this again by the here. And the claim here that this story is quasi-isomorphic metric algebra of but and this is stable isomorphism.
Stable with respect to
The dimension of V goes how it works, because what kind of isomorphism? So there is a map from downstairs to upstairs, because the elements we draw the graph. Some outputs that's before and attaching several inputs, several outputs, and then with each such a graph, we have an operation from the collection of polyvector fields. The polyvector field precisely in the same way, just contracting taking the traces, contraction of the indices. So for each graph, if the graph has directions and inputs and outputs, there is a map from here to here. Polylinear map. Yeah, so for each from this gamma gives you the map from lambda the number of vertices. Now, if in order to be the isomorphism between those kind of maps to the space, you need that the dimension of V will be infinite. What does it mean? It means that there is no relations on the traces. So you don't allow, because the relations for the traces appear when the dimension of the space is less than the number of trace of which power you are taking. The Hamilton equation gives you the relation when the dimension of V is big enough. So therefore, this is precisely stable, means that if you are thinking that there are no relations on the map going from here to here. So therefore, you can do it combinatorially instead of working with this story. You can consider the graphs, but of course, a priori they may be disconnected. So this symmetric power means that you consider so this is a connected component, because it happens for each connected component separately. So you can look on each connected component separately. So this story is that the additional term that is taking the connected component of the graph. And the remaining story is that this graph complex, is isomorphic to the complex where you allow this kind of orientation. So there is a quasi-isomorphic that shortens this direction. So there are two. So this one is a bit bigger, of course, because you have many possible different orientations, but this is smaller, but the statement is bigger.
For the difference here on the left, you don't have fixed orientations. So what was the difference?
Yes, the difference here you have fixed orientations and you have.
And there you don't have orientations.
Yeah, here you don't have orientations at all, and you don't have additional half angles where you play this part of the.
Here you say this kind of full graphs with oriented edges.
No, but then you go down. But
I just know that.
Finally, they're each representative of the story. So the presentation depends on the sign. Depends on the sign. So the statement, these two complexes are the same. So therefore, if you look on this T-poly, you will get something which is more or less a graph complex.
It's like the computation of polynomials somewhere in the respect after the end respect of the
Yes, it's the same computation.
canonical syntax.
Yes, that's
So you have some kind of weight class there?
no, because weight class disappears when the dimension
I
goes to infinity. That's the
I
point.
see. Because in all dimensions it exists.
Yes, it exists all but it exists in more and more dimensions, right? So it starts from
So usually the dimension is 3. It's 3 gamma, which
so this is the separate story. No,
That's-
there's that story really for that story it's really important the dimension of yours. And here the dimension goes to infinity, and you are looking for functorial maps, so maps where you can substitute for each particular. Now the one more result that I want to mention here, when we finish, is that the set here T-poly contains T-poly 0, which corresponds to the number of inputs is equal to number of outputs. So this T-poly. Where precisely the quadratic Poisson structure take place. So the theorem says that if you consider then it's also once there's a work to the total. And which means that on the level of graphs, that means that you may consider the graphs where for each vertex number of inputs and number of outputs is equal. And the non-trivial combinatorial statement is that this complex is quite isomorphic to this complex up to some one class. That's why I'm saying that quadratic Poisson structures are as rich as the full Poisson structures. So those deformations here of those is really as rich as let's see. Okay, so I think that at the moment it's better to stop because the next part will be about the deformation quantization.
in the next part. I suppose. So, because actually, we can arrange for another talk.
No, not this. Not next time.
Other questions or comments concerning the
Everybody's time to
also
know about graphs.
we have I know that one quantization in a linear case, it's also just universal American algebra. Actually, such this quantization is quite unclear. I mean, it's about universal American algebra depends a lot on this construction. So just wonder whether this this kind of graph like it's about inside universal American algebra So those are
No,
two separate-
this is the first step in the computer. So you see these graphs is just the way how you can compute the size of the deformations.
Yeah, I see.
Not the directly the deformation itself, but only the size. Because the problem for those computations that this graph complex is really a complicated story. The
Yeah,
cycles in
definitely.
this graph complex are really
Yeah.
really something incredible. So
Yeah,
the
that
only
is.
thing we know is just we know some first examples, and you see that each computation, each action is really complicated story. So that's really this is just the way how to to give some bounds on the size of what kind of deformations you have, and just identifying the deformation of one object, one mysterious object with another mysterious object. So that's it. So you can say that this one is equal to this one, they're quite isomorphic, but we are not able to compute neither this nor that story. So this is only just the way how to attack. So that there are a lot of attacks that just to understand the destruction of the laws.
So
It's
not
far from being done.
it's not about the deformation of some particular example, but it's talking about.
It's about
size.
universal deformations.
Yeah.
About the size of universal functorial deformations. So not about the particular deformation itself.
So, for instance, so it cannot be used either for deformation of, say, so it's supposed to have two Poisson structures and you have a morphism between them, not to use that here either.
Yeah, if you want to do it directly, you really
Yeah,
get huge computations.
again.
So it's on the most low level cases it's
Already
possible, but still, even trying to apply this tetrahedron
Yeah.
story to a Poisson structure, as I said, I never seen that someone was able to compute
Yeah.
till the end, because here it's about 8 terms.
And
you
the
have to-
terms will be 64.
So it's really, yeah.
I see.
So
Okay, any other questions or comments? Maybe on.
I have one just technical question. You mentioned at the beginning some calculations of granular basis. Do you have some special programs for that? Or it's just, or you just didn't do such calculations by computer?
No, in this case, I was able to do them by hand, because the problem here is that for the computer, they are really complicated. Because you need too many generators and too many relations. And the problem is with these graphs that they grow exponentially. But in some cases, so we have program, not me, but my course, Volodya Datsenko, has a program that allows you to compute the granular basis for operas and for some operas with not big amount of generators, not big amount of relations. It's really a box, so you can get some results.
Is it written in some package or in C++, or what is the kind of?
If you go on his homepage, then there is a package in Haskell.
In where?
Go to the page of Vladimir Datsenko. It has some packages written, but unfortunately not on the Python, but on some other.
Not on the Python, but where?
Not in Python, but in some other language.
Okay. Sorry, but the sound is too bad still. Okay.
Okay. I'm not able to work on this story. I'm always asking to with Volodya computers.
Yeah. It's always good to have a friend like that. Is able to do something.
Well, unfortunately, not always he is time for this.
Yeah, sure. Okay.